Well, we've lost a couple already.
Yeah, yeah. Well, that was he was in here doing a short test for the
Oh,
building
okay.
side of things.
Yeah.
Yeah, and then the couple of commercial people that are here, they were running through some stuff with Merrin before they come in. So
Yep.
so that was me.
Did you want to wait or did you want to?
No, I think get into it.
Okay, no
Yep,
worries.
no conflict. Yeah, and that was a bit sitting around.
Yeah, no, good, good. Because I was looking at.
Do that, so.
I've got a piece here, but that's where I can leave that. I can leave it in the bottom there and just use this one here. All right, good stuff. Well, I'll carry it on then if you.
Yeah, great.
I'll just make this a bit bigger. Okay. What I'll do firstly, if I can, just so I can. Now I know this this presentation is basically designed for sort of graduate architects.
Yeah.
So it is a CPD point presentation. So there are continuing professional development points that are associated with this presentation. But just so I can justify it with my employers, being Kingspan, can I just get you guys to put your names on here? And then what I'll do is I'll kick it off if you like. So, like I just mentioned, this presentation is designed for graduate architects. It really is more of an educational presentation that really just talks about what insulation is, how it is measured, different types of insulation, different applications as well, and just the way that heat sort of really transferred and sort of conducted as well. So. Just jump into it. Like I said, there are some learning outcomes, and they are to the thermal insulation basics, material R values versus total R values as well. It's the U values and K values. So everything virtually has a K value, and the K value sort of really stands for the conductance of heat passage through a material, which we'll talk about that as we go on, and types of insulation materials, and then just different ways that knowing your insulation companies and just different ways that people are able to help you as well. So firstly, just to understand how thermal insulation works, describe the differences between total and total R values and material R values, and identify the K values. So do a double up on that one. Just to give you a bit of background on myself, I'm James Pinion from Kingspan Insulation. Been with before this job, I was a roofer, so I was in the roofing background for around about 8 years previous to that as a roofing contractor. So I've had a fair bit of experience installing insulation, installing roofing as well, of course. Been with Kingspan now for 14 years, so I have a pretty good sort of understanding of the insulation industry, so hopefully I should be able to answer the majority of your questions. And if not, we normally find out what those questions are and the answers, and we get back to you. So just Kingspan as a glance, we have an environmentals division that Mike and I were just talking about before, which is our rainwater sort of harvesting, so collecting of rainwater, grey water, solar voltaic panels, heat pumps, wind energy. We have an insulated panels division as well. So the insulated panels division is pretty much like a roof sheeting. Thanks for that. Is a roof sheeting with insulation and then roof sheeting on the other side. So it's a structural insulated panel. So we have an insulated panels division as well. Have an access flooring division, which is a really cool flooring part as well, whereas you can actually have a raised flooring section where you can actually run data cables and services underneath the floor. You can sort of pop them up, underneath your desk or where you need them to be. So. Quite a unique product, that one there. And then of course our insulation division, and that's what I pretty much will look after, and that's what I'll be talking about today over the next, say, 30 to so minutes. So now Kingspan's got quite a few manufacturing plants around the world. We've actually got quite a few sales offices around the world as well, but just recently, I think this slide's a little bit dated, because just recently, around about 2 years ago, we just finished our manufacturing facility in Somerton, Victoria. It is a $43 million investment. So this is a unique, state-of-the-art, dedicated manufacturing line that just manufactures our rigid insulation, which is our cool therm material, and I'll show that as we go on. And we also have another manufacturing plant in New South Wales as well, where we manufacture our air cell product. So I'll give you a bit of info on that as we go through. So this is our plant in Somerton, Victoria. This is going to be the first Green Star manufacturing facility in Australia. There's plenty of Green Star buildings around the place, but as far as manufacturing facilities go, this is going to be the first. So at the moment, we're running 2 shifts. On top of the roof, we have solar voltaic panels that's generating their own electricity. So being able to generate your own electricity and run your shifts without any sort of pull off the grid, off the electricity grid is fantastic. So at the moment, the building is pretty much all manufactured from all kingspan type materials, of course. There's some insulated plasterboard in there, there's kingspan panels in there, there's some air cell in that building as well, and as well as the tanks. So just to jump into the basics of insulation. So insulation will pretty much move in 3 ways, and you will get 2 types of heat gain. You'll get heat flow in, which comes in the summer, so the heat flow coming from the sun coming into the building, and that's either referred to as, say, heat flow down or heat flow in. And then there's heat flow out, which is heat sort of escaping the building. And the purpose of having insulation is to try and minimise the heat getting into the building in those summer months, and to try and stop that heat exiting the building in those winter months. So trying to get a good balance of both of those type of insulation is something that needs to be sort of considered, and that's what we'll sort of really go through today. So heat is transferred in 3 ways. There are radiation, there's convection, and conduction. So if you imagine like a hot cup of coffee or liquid, the heat sort of escaping out of the top is the convection. So if you were to hold your hand over the top and you can feel that sort of steam coming up, that's the convection. It's actually warming the air above. If you sort of held your hand close to the cup, you'd feel the sort of heat radiating out. And if you actually touched the cup, you'd feel the conduction. So heat will sort of transform in three different ways. Probably one of the most common insulation that you'll see out in the market in the building industry would be bulk fibrous insulation. It's normally glass fibre insulation. Now the way that works is it's made up of, and I'll just use this whiteboard if I can, that's all right.
Sure.
The way that works, this
Yeah,
sort of
that one's a bit dry. Yeah. Well, use this one. This one I know is not dry.
Yeah, okay. No, I don't want to leave any permanent marks. So the way this insulation works is basically it's made up of thousands of strands of glass fibre. And it's these air pockets all in between these glass strands of fibre that really reduces the heat transfer through that material. So, so really it's just having the actual bulk insulation coming through that material, and that slows the heat transfer going through that material. One thing to consider, and we'll talk about this as we go on, one thing to consider as if you have just a bulk of insulation on top of your ceiling in a very hot climate, eventually all these air pockets will heat up, and then you'll have a mass of hot insulation sitting on top of your ceiling. So, you know, a lot of people would get home from work, you know, 5, 6 o'clock on a 35-degree day, and they'll find that the house is very hot because the insulation on top of the ceiling is a massive insulation, and it's started to heat up and it's holding that heat. So that's why it's important to get a good balance of insulation. Another form of insulation is rigid insulation. So rigid insulation is, we manufacture one, it's called cool therm. It's made from a phenolic resin. It's a rigid board insulation. Some of the benefits of having a rigid board insulation is they won't sag over time, and this actual phenolic resin has actually got quite a good R value for its thickness. So for every 20 millimetres, it'll give you an R1. Mm-hmm. So I'll just pass that around if you want to have a quick look at it. Another type of insulation is reflective insulation. Now, the reflective insulation really works by reflecting the radiant heat. So it has a reflective foil on the insulation. The radiant heat is reflected off of the reflective foil, and then the remaining heat, or some of the remaining heat, is sort of slowed down by the material in between the two layers of foil. Now, for this reflective insulation to be effective and to work, you really need an air cavity. You can't have it hard up against your iron roof or your tiled roof or your wall. You really need a reflective gap to have a reflective air cavity. Otherwise, the material itself will become conductive as well. So, give you an example of some materials that are poor sort of insulators, and they're more like solid products. So, such as concrete, brick, metal, glass, materials that don't have a lot of air in them. So, products that are solid, they're classified as poor insulators or good conductors. Thanks. Materials that have good insulation properties will be those materials that do have air within inside the materials, so more lighter sort of products, such as fibre, like we saw before. You had your fiberglass insulation, rigid insulation, such as the Cooltherm, air cell, and even still air is a bit of an insulator as well. What I probably should have said was, and heat will naturally flow from warmer places to cooler places. So, a bit of a quiz there. So, I'll answer that first one for you. So, talk about R value. So, R value really is the resistance of heat resistance. So, the heat being resisted through a heat passage. So generally, the higher the R value, the better the system would work. So the idea is the higher the R value, the better the insulation is going to be effective. And the idea of it is to reduce the greenhouse gas emissions and make the building more energy efficient. So there are two types of the way the R values are really considered. And if you're looking in the National Construction Code, they really talk about roof systems and wall systems and floor systems need to achieve a total R value. Oh, sorry about this, guys.
And that's the summary that I've put up there for those. I've mentioned that to the couple that were in a little bit earlier, but I've put up a bit of a summary here of the NCC and the required R values for your wall and for your roof insulation for your various different climate zones.
Yep, yeah, excellent.
So we've got both climate zone 4 and 5 and climate zone 6, where, you know, depending on the reflective surface of your roof, how much heat would be drawn in there, and there's the reflectance values given in the NCC, 4.1 to 5.1. So 5.1 is for your darker roofs, your blacks, things like that. And then in climate zone 6, 4.6 and 5.1 for those. And then typically R2.8 for your walls.
So thanks, Mike.
That's
so
right. Yep.
just on those, so basically those walls, roofs, and if it's an elevated floor, so if it's a suspended floor, that will need to achieve an R value as well. Now the R values that Mike's talking about are total R values, and that's what the National Construction Code will ask for, total R values. But total R values is the whole build-up system. A product R value will be the R value of just the product itself. So, for example, a 90mm fiberglass vat, 90mm would be around about an R2.5. I mean, you do get higher densities as well, so it can change, but around about R2.5. 20 mils of Cooltherm would be like R1, for example. So the product R value is the R value of the product itself, and the total R value is the whole build-up system. So we'll go through that and see how that works. So the added R value, or the product R value, is the product's thermal resistance, and the total R value is the product's thermal resistance as a whole. So it's the building materials and the thermal resistance of the whole system. So, for example, if we had your iron roof, your reflective air cavity, air cell insulation under your iron roof. So we had your iron roof, air cell insulation, a 40mm reflective air cavity, a reflective attic space, and a 10mm ceiling. The total R value of just your air cell, let's say in a winter condition, would be R1.4 as a total R value. The actual product of the R value is much less than that. But if you were to add, say, an R3 insulation on top of your ceiling, the R3 insulation, the product R value of that is R3, of course, but the total R value of that whole build-up system would be like R4.4.
Will you be able to tell me how to calculate the R value, like, general sense of how to calculate it? Like, is it kilojoule divided by something, intensity or something?
Yeah, okay, yep. So we'll talk about the K values. Yep.
R value I'm talking about.
Yes, so to get an R value, everything that's got a K value, so you've got to divide that by its thickness. So yeah, we will go into that. Yep, I'll go into that. So just to touch on this point here though, so it's the products that are put into your wall and your roof and your floor systems. It's the insulation values that are put into there, in combined with your what air cavities, what sort of walling material, whether it be brick, whether it be Hebel, for example, whether it be FC sheeting. So depending on what actual building materials you're using, the whole lot put together is calculated to give you a total R value. But the products on their own have their own R value.
That's called material R value.
The material R value, that's correct. So this system here is a total R value system. So this will be a good one for you. What's the difference between a product R value and the total R value? Any takers for the answer?
Yes, product R value, talk about the insulation amount that.
Yep, you're right.
Regards to the material.
So the product R value is of the material itself, and the total R value is of the build-up system.
How does our standards compare to the overseas standards?
So overseas, for example, their energy efficiency requirements are much more higher than what ours are.
Yeah.
We're still playing a bit of a catch up as far as what they're doing throughout Europe and the US and even in New Zealand, for example.
It's just basically the same like we Ford Holden cars with rate, and when we should have been driving Mercedes.
Well, I mean, over some of those colder climates, the conditions are a lot more sort of extreme. So they've had to deal with the insulation issues a lot sort of earlier than what we've dealt with them. So
how do they go in the tropics though? Because do you really want insulation in the tropics?
Well, that's different. The difference now is in the tropics. I mean, there's your typical Queenslander type sort of houses,
Yeah.
or your Northern Territory type sort of construction, and they've always been to sort of build the houses with plenty of cross ventilation, so you can open up windows and doors or screens and have some air sort of blowing through the house to try and keep them cool, or keep the house as close to the ambient temperature as possible. With the new energy requirements coming out now with the software packages like your First Rate 5, your Burst Pro, ActraRate, what they're doing now is the only way for them to really get a 5 or a 6-star energy rating is to be able to close these buildings up. So you can't really have these tropical type sort of buildings up in those areas anymore. Now you need to really close them up and put insulation in there, like Mike was pointing out before. The National Construction Code says in your wall, you need at least an R4.6. Sorry, in your roof need at least an R4.6 or 4.1. In your roof need at least an R2.8. I mean, so you can't really get around those energy efficiency requirements now. So the only way they can do it is put insulation in there, close the building up, and then try and air condition it. And that's what most of the houses are doing. That being said, Northern Territory, for example, is still working on, I think, 2009 BCA requirements. So they only really need to achieve an R1.4 in their walls, as opposed to an R2.8. So.
Yeah, and also, not that I know much about the tropics, because teaching for climate zone 4, 5, and 6 here, but. Your climate zones up in the Northern Territory be climate zone 1 and 2,
yep,
and
climate zone 1, 2, and 3.
Yeah, so there are different requirements under the NCC
Yep.
as well for those than what we deal with here.
Yeah, that's correct. Yeah. So very top of Australia is basically climate zone 1, and if you go all the way to climate zone 8, where we places like in Tasmania, for example, and places in Victoria like the alpine areas where it gets very cold, and you need much higher thermal values to be able to try and stop that cold or try and stop that heat from leaving the building. So talk about U values and K values, and this will hopefully answer your question, and we'll talk more about this as we go through it. So basically, the U value, so the R value is the thermal resistance of a material. The U value, so just read it properly, the insulation material's resistance to heat passage. The U value is the thermal transmittance, so the amount of heat that's transmitted by the insulation material. And it is pretty much, it's the inverse of an R value. So a U value is 1 divided by the R value, or the R value divided by the U value. So just have a look at that. Probably the most important thing is to remember is probably the K value, or the conductance value. So everything will pretty much have a K value. So for example, if you were to get our cool therm, what they do, the way they measure it, that they get a K value, is what they have is they have like a hot plate test, and they do this inside of a lab. So they'll have a plate which I believe is heated up at 18 degrees. Then so they have a plate heated at 18 degrees. They'll put an insulation material on top of the hot plate. They'll put another hot plate that's heated up at 24 degrees. Then they'll have a temperature prong go into the very centre of it, and they'll see how long it takes for that temperature to reach a medium of, say, 18 degrees. Now, through that, there's a mathematical calculation and a method that they use to arrive at a K value. But once they've got that K value for a product, you can then divide the thickness of the material by the K value to work out what an R value is. So, for example, the K value is the physical property of a material to express its ability to conduct heat regardless of its thickness. So the thickness in meters divided by the K value. So for example, the K value of cool therm is 0.02. If you did a 50 mil thick cool therm, which would work out in meters, which would be 0.025, divided by 0.02, which is the K value, that would give you the R value. So probably should run through this. So a 50 mil rigid thermoset phenolic resin board has a K value of 0.02. So what is the R value and what is the U value? So if we were to do that on the board, so pretty much the actual thickness. So the actual thickness is 50 millimeters. So so to work that out in meters, it would be 0.025, and then that's basically, you need to divide that by the K value. 0.025, yeah. So divided by 0.02, and that will give you the R value. Do you work that out?
Yeah, the numbers are actually small, so you know, with just having a number, it's not comparing it. So with a normal house wall insulation, how does that compare to a cool room? Like,
okay, so first, before we move on to that, the smaller the K value, the better the R value. So the K value is going to be the inverse of the R value. So the smaller the K value, the better the R value. So if I...
So we've got R value of 1.25 of that.
we should have...
Yeah, 2.5, shouldn't we?
Yeah, we should have 2.5.
Yeah.
So pretty much, if I just get to my calculator here, and I'll just... so pretty much, so 0.025 divided by 0.02. I've got it the other way around. 0.02 divided by 0.025 is our 2.5. Divided by 0.02.
So that comes from 20. That comes from
No, that's 1.25.
Yeah, 50 millimeters. Yeah, so yeah, yes, yeah, but
0.05. No.
0.05. Yes.
No.
Yeah.
Oh, yeah.
0.2
Yeah.
divided
Yeah.
by
Yeah.
I don't think that's
Yeah. Yeah. Yeah, James. I think the 50 millimeters as expressed in meters is 0.05. I think that's how we.
yeah, it's better. 0.05, yes. Divide that by 0.02. 2.5. Yeah. So 0. Yeah. So we have to get rid of these two here. So 0.05. So just get back to what we were saying with the inverse. So the K value being the inverse of an R value. So the smaller the K value, the higher the R value.
Yeah.
So if you talk about cool room panels, I think traditionally in cool room panels that they've used like an expanded polystyrene, for example. And let's say if you look at something like a 200 millimeter expanded polystyrene, that would generally give you like an R3 to an R3.5. So quite a high R value. I mean, they're basically making freezers at those buildings. So
yeah. So you know, is it ever going to get to this setup where this type of wall with insulation is going to basically be like a monocoque construction? So where you'll have the cables running through it and all your power and all that. And
yeah, they're doing that type of construction at the moment.
Like in terms of SIPs.
Yeah, they're doing that type of construction at the moment.
Yeah, because obviously the energy efficiency is going to be a big thing in the coming years.
Yeah, I think it really comes down to the amount of finances that people are going to put towards the building. There's a lot of different ways to build a building, a lot of different sort of methods. I mean, the most common one we're probably seeing at the moment is sort of a brick veneer type sort of construction, and that's probably the most common residential type construction at the moment. But there's plenty of different other ways of building, and that's just about it, sort of exploring, what's available out there in the market. So the R value for the 50 mil was R2.5. The U value is 0.4, but the K value, like I said, was 0.2.
So yeah, so the smaller the K value, the higher the R value.
Higher the R value. So, yep. So thermal bridging and thermal break. So thermal bridging was something that sort of was really talked about, in 2006. That started to come into the market, and it was really for steel frame homes. So they really started talking about what they originally had was they're trying to work out how efficient was a steel frame home as far as energy efficiency goes, as opposed to a timber frame home. What they basically did was they pretty much had a timber frame construction. They put an R2 bulk insulation inside the timber frame construction. They had an FC sheeting on the outside, R2 insulation in between the stud, and an and a 10 mil plasterboard on the internal. So they measured the R value of that, and they came to the fact that it was achieving an R1.8. So although you had FC sheeting on the outside, R2 insulation, and then 10 mil plasterboard, they still measured the R value as an R1.8. So what they were saying was they were missing. The actual R value was reduced slightly. They built a steel frame building. They had the same type of construction, but it was a steel frame building. So they had FC sheeting, R2 insulation in between the FC sheeting and the plasterboard in the steel frame, and with the R2 insulation, and they measured the R value, and the actual R value was actually an R1.2. So it actually had to reduce quite a fair bit, because with the timber construction, there was a little bit of heat gain through the passage of the timber, but with the steel construction, there was a lot of heat loss in between that passage through the steel. So what they then started to do was, they then started to pack out in between the FC sheeting and the steel frame. They started to put timber battens on there, and they kept increasing the timber batten until they got that steel frame building to achieve an R1.8. And then when they got that timber frame, that steel frame building to achieve a 1.8, what they decided was, now the two walls are achieving the same R value. They then got that timber batten, they measured what thermal value that timber batten was, and that timber batten at 12 millimeters worked out to be 0.2 of an R value. So what they said then was, any steel frame building needs to have a thermal break of 0.2 between the exterior cladding and the steel frame of the building.
So that would have been.
So that's why that's when we've had to manufacture the install break. So anything that's in a steel frame building needs to have a thermal break of 0.2 between the exterior cladding and the steel frame of the building. So look at thermal breaks, and basically what it says, it's the conduction of heat through the building elements, such as your steel stud or even your timber stud, but obviously it's a lot worse than steel. And heat will really find the least path of resistance. So very similar to like a dam, for example. So heat's going to find the least path of resistance, similar to what water is going to find the least path of resistance. So the way that it works is you have your metal rafter, you have your iron roof, which is obviously gaining heat through the heat zone, and the idea is to have a thermal break either between your iron roof and your steel cross members. So just have a bit of a look at what heat really thermal bridging really looks like. So this is actually a timber frame building too, by the way. So this is a residential building using thermography in this building here. So pretty much they using thermography. You can see there's some heat being retained on the plasterboard where the insulation is. You can see in this area up here, there's actually quite a bit of insulation missing up here. I'm not too sure what's going on in this corner. Maybe there's a few. Yeah, it could be sagging. Maybe there's a few timbers that are screwed together to support the roof. But you can actually see where the studs are. There's actually quite a bit of insulation that is missing. So the idea of it is to have a thermal break between the exterior cladding and the steel frame of the building, and sometimes even the timber frame. So, bit of a trick question, this one. Timber is more prone to thermal bridging than metal. Well, we know that's false. Timber is less prone. So, but like we mentioned before in the example before, when they had a steel frame building with an R2 insulation, the actual total R value was reduced by a further 0.6. So different types of insulation. There's an air cell type of insulation, basically we refer to it as reflective insulation. The description is a polymer air cell or closed cell foam core sandwiched between two reflective aluminium foils. So that's basically the air cell material here. Obviously this has been on the desk, so you've seen that product around the place?
Actually, no, I haven't shown that around. That was,
okay.
So with our waterproofing stuff, that was in that box.
Yeah, okay, yep.
So I haven't passed it around yet.
How much efficiency would you lose if you didn't have the reflective part of it?
Well, you would lose a bit of. I mean, you're going to lose having the reflective foil there. It's going to stop a lot of the radiant heat gain. So that does make a bit of a difference as far as the R value goes. It's probably going to the reflective properties are probably at around about 0.6 of an R value to the total system.
I've got that stuff in my sight boxes and it works brilliantly.
Okay, yep. So you've got the air cell or just sarking stuff underneath it?
It just I just cut it to size, and I've just sort of fitted it into the lids and the walls. And,
yeah, good stuff. And it's sort of like just reducing. I mean, if you're talking about sight boxes, they obviously will be made of metal, I imagine. So they heat up in the sun and start to radiate a fair bit of heat. So these sort of products are sort of suitable for the under your iron or tile roofs. in your walls and under the floors. We don't really recommend them being on top of the ceilings. So really under your iron, your walls or your floors. So where they're good is, so some of the positives, they're fibre-free and non-allergenic, vapor permeable or they can have a vapor barrier. So if you're using like an FC sheeting on your walls, you need to have a vapor permeable material. So the product you have as a sarking or a reflective foil needs to be vapor permeable. So it needs to be able to let vapor sort of escape, because you can get a condensation build up. Because there's no nesting materials within sort of sarking, you know, that they're good to resist sort of rodents nesting in them as well. And some provide a thermal break, such as the Insul break will give you a thermal break. Some of the negatives, they require reflective airspace. So if you have the product hard up against your FC sheeting, there's no reflective airspace, so you won't get any effectiveness out of the product. All you'll get is the actual R value of the product itself. Sarking, and you've probably seen sarking around the place. It is another reflective foil. However, it actually doesn't have any inherent R value to it. You will get your reflective properties as long as you've got your reflective air cavity. But basically it's just foil laminated paper on both sides. It's also good for under your iron or tiled roof, in the walls and sometimes used in the floors. Some will give you a vapor barrier and some allow breathability as well. So like I said before, behind FC sheeting, you really need that breathability.
Yeah, James, having been a roofer, that's something. Well, I'm not a roofer, but having been in a few roofs, doing all the repair and reinstatement work, I've seen a lot of the sarking actually just hanging down, like older sarking under tile roofs.
Yeah.
Split and hanging down.
Yeah.
Do you know if that's something that's been really improved in that industry, or
I know. It's
in terms of durability of the material?
It's like any sort of products. I guess it's some are poorly made. You know, some are made better than others.
Yeah.
Probably the most important thing to remember is, you know, if you're going to be putting, you know, a material in, you know, you try and go for a good reputable brand. You know, something that's made you know, with a bit of quality. There are quite a few products that sort of make their way into Australia that are less, you know, they have a lower quality.
Yeah.
But yeah, so certainly in some of the older roofs, you do see where the sarking has sort of deteriorated. Yeah.
Yeah, because it's something you can't just go in and easily replace.
It's not easily fixed.
Yeah.
It isn't easily fixed, no. But I said, yeah, I mean, with our material, we give it a warranty of 15 years.
Yeah.
We have life cycle testing, which are essentially a life cycle test that they're actually like they're quite just like big ovens, and we put our product in there at like 90 degrees Celsius. I think at the last sort of update I had, it'd been in there for over like 6,000 hours, which, you know, sort of, you know, estimates it's around about, you know, at least 25 years.
Yeah.
You're gonna get at least 25 years out of it.
Yeah, 90 degrees Celsius.
At 90 degrees Celsius, yeah.
Yeah.
So phenolic insulation, such as your Kingspan cool therm that's made from phenolic insulation. Basically, it's a phenolic core. It's a thermoset sandwich material between two layers of reflective foil. Pretty much this material, like I mentioned before, it's got a K value of 0.2. Every 20 mil is going to give you, say, an R1. So 60 mil is R3. Suitable for, you know, underneath your iron roofs, on top of the ceilings, in the walls as well, even under floors. So you can use it. It does get used quite a fair bit. We use this material quite a lot in the commercial industry. As far as
in the floor,
if it's suspended.
if it's suspended, yeah.
Well, but that being said, we also use it underneath concrete slab on ground as well.
Yeah, because you know everyone walks on concrete. It's bloody cold.
Yeah.
So you know.
So if you have underfloor heating in your concrete, well, there's a requirement to have an insulation value of at least 1.25. So that would be our 25 mil thick cool therm. So pretty much what would happen would, once you've dug out all the footings and the trenches and the forticon has gone down, you then put your cool therm, it's called K3, you put your K3 down, then your reinforced reinforcement mesh would go on top, so the chairs was the chairs to support the mesh would sit on top of the cool therm, the K3. Then your heating would be sort of tied to the mesh, so that's sort of wired to the mesh, so it's all tied in, and then the concrete's poured.
So yeah, so it's vapor membrane.
Yes.
Yeah, vapor membrane, then insulation, and then you.
Yep, and then the chairs.
Chairs and your
to
bars.
support
and
the
your top of your concrete.
reinforcement mesh.
Yeah.
And then the concrete is sort of poured. So that way, as the as the underfloor heating is working, the heat's sort of being forced up, and you've got an insulation layer between the earth and the concrete.
But in terms of the suspended floor, there's a minister's specification for
Yes,
insulation. Yeah, underneath.
Yeah, there is.
Yeah.
For suspended floors, you really need to be achieving an R2 in climate zones 5 and 6, and if it's got heating in there, if it's slab on ground, you really need to have at least an R value of 0.12.
Yeah. So sorry to digress a little bit, but the hanger system for that cool thing, do you have a hanging system that sits over the joists that they sit on, or do you screw this?
Are we talking about what
for
application?
for your suspended floor, sorry.
Okay,
yeah,
for the suspended floor, there's a couple of things you could do. If you had a suspended timber joist floor, so let's say these were your joists, say every 450. There's a couple of things you can do. If you wanted to put the cool therm in there, you'd have to sort of like build basically a batten type sort of system, and then put your rigid board on top of the batten in that system there, so you'd have your insulation in here. Mm-hmm. The other way you could do it, if you had used we've got a product called Permi Floor, which is part of our air cell material. Mm-hmm. That would come in a roll, and you'd virtually just there's a couple of ways you can do it. We can either supply it in a Permi Floor 500, so it's a 500 width, and you can sort of just staple it to the side, and it will staple in here. So that's more of our air cell product.
Yep.
But the idea of the air cell, you still need that. If your floor was here, you would still need this to be a reflective air cavity. Yep. In this area here.
Yep, and that Permi floor meets the requirements for South Australia in 5 and 6.
It does. It does. Depending if that floor area is open or closed.
Yeah.
For example, so yeah. Other types of insulation is what we refer to as PIR. Now Kingspan is a large manufacturer of PIR. Our latest factory though that we built here in Australia, say 2 years ago, is basically we only manufacture phenolic resin, which is our cool therm. The reason being is phenolic resin is the next sort of evolution in materials and chemicals. So PIR is more of an outdated product. But that being said, it is still a good insulator. So it's a rigid board, so it is a high performance fibre-free rigid insulation. So again, it's used in the same applications under your iron roof, in the walls and in the floor. It is fibre-free, does have a good board strength, and some do give you a good vapour barrier as well. Some of the negatives, it's lower performance than the phenolic foam, or the phenolic cool therm resin, and it's perceived to be more expensive than other insulations. So extruded polystyrene, so some of these insulations, they're not really being used all that common anymore, mainly because of the new fire requirements that are coming into the National Construction Code. But extruded polystyrene, for example, was quite heavily used for a long time. It is now starting to be used sort of less and less because of the fire requirements. As you know, anything that's sort of like a foam, like especially a polystyrene, you put a flame to it, or even 90 degrees Celsius, it starts to sort of melt a little bit, lose structure. So, and if it had a naked flame to it, it can catch light and combust quite easily. So, but it does get used quite a fair bit in your roof, walls, and the floor. In the past, like I said, that is starting to change, but it has a low conductivity. has a quite a good material strength to it, but as far as the as a thermoset, it can melt quite easily.
Yeah, one application I've seen used a bit is in gable ends. So because it's it's very simple to cut, and you just get it into the gable end, and then you
Yes.
render over it. So it provides that rigid substrate for rendering.
Yeah, that does get
Yeah.
used quickly. Yeah.
Are you guys doing a phenolic resin board
We,
that acts
we
as a
do
substrate
that.
for render?
That's called our K5 board. So
Mhm.
basically, it's our cool firm board. It is got a bit of a diagram here of different sheets, which I'll pass that around later. But basically, it's we do have a board that we can render. It is either 50 mil thick or 80 millimeters thick. It goes mainly on residential buildings, and you can you do put a render on that as well. So
Mhm.
yeah, we do have an alternative to EPS top fill boards.
Yeah.
Yeah.
And what's the weight like? Obviously, it must
It's
be very
light. It's quite light. It's a 50 mil board would be around about 2 kilograms per square meter. So it's quite light. Yeah.
And is that, does it class as non-combustible, or it's
No,
or
it's not classed as
yeah,
non-combustible. So you
it's
do need
still,
to be careful like where it is being used.
Yeah. But it's not as flammable as
No, correct. Yeah. So you
polystyrene,
can put basically you can put a blowtorch on it, and you won't get any sort of melting or distortion in the colour. You will get some charring. So the outside will char, but once but you're not going to get that melting or combustion like you'll see. But that being said, it's not classified as non-combustible.
Yeah, because that Australian standard is very hard to meet.
It is, yeah. The 1530 part 1, it certainly is. So expanded polystyrene, again, it's a very sort of similar material, but it's basically your foam products. Again, as far as insulation goes and building materials, they are being used less and less now due to the fire requirements. But a lot of the benefits are the same as what was spoken about. So again, one of the most common insulation that you're going to see out there in the building industry at the moment is your glass wall. So that's being used quite a fair bit on ceilings, in walls, in wall studs as well. And you probably had some type of sort of exposure to that already in your either when you're doing renovations or you're building something. So basically, it's a molten spun glass fibre bonded with our resin. Suitable for the ceilings, walls, does get used in the floors a fair bit as well. Now this one is classified as non-combustible, but it does depend on the density of the material. As you get a more denser product or a denser material, and you start to add more sort of binding resins, then it loses its combustibility. So it's it's something that you don't want to just refer to as non-combustible as a blanket type sort of statement. But typically your 90 mil bulk insulation would be classified as non-combustible.
Yeah,
but it might be a little bit expensive than other materials.
No, this one here would probably be probably more cost effective. You know, it probably works out to be $7 or $8 a square metre. So that's why this one's probably more commonly used in the building industry. You know, it's pretty well cost sort of effective. It gives you the R values you need, and in most building studs at the moment in houses, the studs are generally at 90 mil thickness. So it's made and fit for purpose.
I guess
all the insulation, that would be the last thing I'd use. You know, I've been up in my room, and I've within 5 years, that was so dusty. And if I didn't go up there without a mask, you just wouldn't survive it. For those people that have got hay fever, asthma, that should never go in a house.
Yeah. Well, everyone's got their own thoughts on it. So I mean, that's correct. I mean, we get phone calls a lot of times where people do have allergies and that type of thing as well. So they're looking for alternatives to be able to insulate their buildings without anything that's got good fibres associated with it. So.
But I think one of the the major limitations on it though is the style of roof that you're doing as well. So if you're doing some skillion roofs or a raked ceiling where you don't have a great deal of depth in your ceiling, sometimes there's just not the space to achieve the required R values with the bulk insulation. I think
Yep.
is the main
Correct.
the
So
main driver in those
so
choices.
so just on that, we actually use our insulated plasterboard quite a fair bit on those those type of construction styles. So on a raking ceiling, so basically it's our phenolic resin with plasterboard that's actually laminated to it. So that material can go up as one sort of panel. So the beauty of that is it'll give you a continuous insulation. Again, it's a good insulator and it's got plasterboard already attached to it. So that gets used quite a fair bit. But you're right. I mean, with fiberglass material, it does have it can get dust on it, so it does have fibres associated with it. It can get brittle. It can settle and slump over time as well. And but you know, some of it can absorb the moisture as well. So rock wool is a material that gets used quite a fair bit. This product here gets used in the walls, under floors. It does get used in roofs a fair bit. Rock wool is pretty much sort of considered as non-combustible because it's sort of manufactured out of pretty much essentially a rock. So it's excellent for acoustics. Some of the negatives would be fibres. So it does have fibres associated with it again, or manufactured from fibres. Can be brittle. It can get brittle, settles and slumps over time, and they can absorb some moisture as well. So some other insulations that get used, typically when people do have asthma and those type of things, would be a polyester. So the very same material that might be in your pillows or your quilt, that polyester product, they get used quite sort of widely in that type of construction areas. So they get used quite a fair bit in schools. Quite good for the ceilings, walls and under floors as well. Some of the benefits are it doesn't settle or slump, so it sort of stays at its full loft. It's non-allergenic as well. It's sort of odorless, low VOCs. Some of the negatives though, as polyester, if it's exposed to heat, it can melt. If it's exposed to a naked flame, it'll catch fire and it can burn quite easily. So. Probably one of the older type of insulations that gets sort of retrofitted into existing houses would be your cellulose. So basically it's made from sort of waste paper, gets pumped into the building. So it's easy to sort of pump in. A lot of them have fire retardants. Trouble with some of these products is that they do sort of settle, they can absorb moisture. And some of them can actually, what they call is migrating. In tiled roofs, you can get quite a sort of a breeze in there, and you can go up the roof. Sometimes you can find on one side of the wall that you might have 2 or 3 feet of this material, and in other areas of the house, it actually gets quite windy inside inside the tiled roof. So
it'd be a nice home for Vernon though.
Yes, you would think so, wouldn't you? Now, if you had a double brick cavity wall and you needed to retrofit, so pumping in a cellulose material would probably be the only solution there. But there is a graduated rock wall. It's meant to be sort of encased with little bits of silicon, so you don't get water sort of ingress from one side to the other. So mainly between double brick sort of leaf cavity walls, it would get used, and it's the only product that really can be retrofitted into double brick cavity.
Is it cost effective?
I'm not really too sure on the cost of this, but you need to talk to the insulation. Some of the insulation companies that do offer this. I mean, Kingspan doesn't offer this type of insulation.
Yeah, but that's the issue with insulation. Very little of it can be retrofitted.
Yeah. Again, our insulated plasterboard, I mean, double brick cavity walls, their insulated plasterboard can be fixed to the internal. So that's one way of doing it. So as far as R values go, to achieve an R3, Kingspan would do it in 60 millimeters. If you had polyester, you had to 100 mil. Polystyrene out to 100 mil. As you sort of go down the line, you can sort of really see polyesters out to 185, so you need much more thickness to achieve the R values. Oh yeah, one more quiz break. Which type of insulation has the lowest conductance per millimetre? With the phenolic resin. So just ways that we can help. We can give you design and CAD drawings off of our website. Also give you custom sort of solutions to meet the Section J requirements as well for your energy efficiency provisions. Which they're basically thermal performance calculations. So at the moment, we'll list all the actual elements within the actual wall or the roof, list the elements that you're using to make it up, whether it's brick veneer. So if it was a brick veneer, for example, it might look like outside air film, 110 mil standard brick, 50 mil air cavity, because that's generally the air cavity between the brick and the stud. Permacav, so air cell permacav, R2 bulk insulation, 10 mil plasterboard, and then internal air film, and then we'd give you a total R value of what that R value comes to. So we can give you those thermal performance calculations.
When you calculate the thermal performance calculations, do you consider about ventilation?
Ventilation, yes, we do. So depending on the, whether the floor area or the roof area was ventilated, we'll either have a non-ventilated roof cavity or a ventilated roof cavity. In a brick veneer, it pretty much will all be considered non-ventilated. Although your bricks do have vents down the bottom, or they have weep holes down the bottom, the weep holes down the bottom wouldn't be considered big enough to be vents. They're really there to let moisture escape if you get that condensation built up inside your wall. So under a floor, for example, just go back to this one. So just moving a bit quick on me, this one. So we also give warranties with our products as well. I'm just trying to get back to that design drawing. So yeah, she's not going to stay there. So basically, yeah. So we do have these basic design drawings. So available either PDFs or DWG drawings. So yeah, the warranty process, and a great sort of technical team as well. So if you have any questions, give us a buzz, or give our technical team a call. They'll be able to answer sort of any questions that you have. So
what's the most energy efficient built house now? Like we all build into the NCC, but if someone came out and sort of said,
you really want to be looking at ways of creating a continuous insulation.
yeah. So
an insulation barrier that doesn't have breaks or gaps in it.
Yeah.
So the Cooltherm K5, as we talked about before, the one that has a render over it. So that's basically a cladding that goes on the outside of the building, wraps around the entire house, and then you put a render over that. So because it's continuous, you don't have any gaps in your insulation. That's the best way of having an energy efficient building. Yeah. So have an insulation product that doesn't have gaps in it.
Yeah, I guess when you think about energy efficiency, you really have to look at the house in a really holistic sort of manner. It's not just about the insulation, it's not just about the glazing, it's not just about the orientation or the thermal mass. It's how all of those things work in concert, and that's
correct,
yeah.
It's like having double glazing and feeling good.
Yeah.
So you've got to have the whole package.
That's right. Yeah. So I mean, like you mentioned, like having the orientation. I mean, if there's a lot of windows, are those windows facing north, for example? If they're facing north, that way you get more of the winter sun as opposed to the summer sun. I mean, the summer sun sets in the west, so if you've got a lot of windows facing west, those afternoons it's going to make that house very, very, very hot. So, and where are the living areas in that house? Are the living areas in that house facing west? So the bedrooms at night time are going to be quite hot. So that they'll need quite a fair bit of air conditioning to cool them down. So
yeah, it's a shame Doug's not here because Doug got a house that he's building at Normanville.
Oh, yeah.
It's got up to that 6-star rating.
Yes.
But, you know, he's got very special insulation out from the States.
All right.
Was
Yeah.
it a gel or something?
Yeah, it's phase change material. So the reason he had to use that phase change material in there is because he got a well, I'm speaking for him, but it's got a black roof and very little space
Yeah, okay.
for that insulation.
What was it called? It was called.
Well, it's a phase change material, which is it's like I don't actually know the one that he's used. I haven't quizzed him on it.
Yeah.
But I think there's another product called Aerogel which does
Okay.
the same sort of thing. It's this gel stuff which is in a packet. It takes up heat when there's a lot of heat supplied to it, and then when that in the evening when that that sun is no
Yeah.
longer shining, it gives out that heat. So
It releases the heat.
yeah, and so it changes between a liquid and a solid,
Really?
in certain degrees
Okay.
to be able to do that.
Yeah.
But I think you pay a lot of money
A lot of money
for that,
Yeah.
for achieving that. So
Yeah.
Yeah.
With energy rating, with so we always look at 5 stars. How did it ever get to 6 stars?
Oh, well, just as the energy requirements are just getting higher and higher, and I mean at the moment, there are companies around the place now trying to build a 10-star house. I know Sustainability House are working on a 10-star house at the moment.
What's the highest rating house in the world? Obviously.
Well, at the moment, our program only allows us to get to 10 stars.
Yeah.
Only 10 stars at the moment.
What about the European system?
I'm not too sure. I'm not too sure about what they're doing in Europe. I'm sure that I know they have a lot better building sort of ideas than what we do. I mean, if you look at grand designs, for example, you can see now a lot of them are using rigid boards on grand designs because they're trying to insulate the building in that continuous sort of nature.
Oh, yeah.
Because when you're using a structurally insulated panel like that, which is like a sandwich of wall sheeting, insulation, external sheeting like that, you don't have any studs in between there that have that point of conductivity. So it's a continual insulation. But some of the limitations around that are that for you, if you're going to be doing skilling roofs and things like that, still the SIPS panels that are available still don't meet those R value limitations within the NCC. So you've got to include other elements to be able to.
So a lot of those type of constructions, for example, I mean, one of the talks that we give is on continuous insulations. So and we achieve that by either using the air cell or the cool therm. I'll just go through a few pictures. I'll see if I can get just some that's got. I'll just pass it out of there, perhaps.
Oh yeah, sure. Actually, I might need that mouse.
Oh yeah.
So back into the PowerPoints. Oh yeah.
Yeah. I was going to just see what sort of pictures were available. So the continuous. I'll just get over here if I can. So I can use
sure.
this. So the continuous nature of the house. I mean, if you look at this one here, for example. So what we have been doing is talking to people about having a continuous form of insulation. So if you look at a typical stud wall, you have quite a lot of gaps in the actual insulation itself. So having a continuous form of insulation is trying to minimise those gaps. So not only do you have these gaps, at every 600 millimetres, you also have a pathway where you have thermal bridging that can come through. Now obviously this one's timber, and we know that steel is a lot worse, but you can still lose some heat going through that timber. In steel it is a lot worse, but there's still sort of gaps in where the steel is. So just being able to sort of find ways of disrupting this pathway of heat is really the way to go. So in most areas of the world, such as throughout the US, throughout most of Europe, even in New Zealand, they take that thermal bridging or non-continuous insulation into effect. In Australia, we're looking at doing that in the next release of the National Construction Code, which will come out 1st of May 2019. So we're
updating it for
Yeah. So basically, there's all these sort of areas here that we're really trying to be able to insulate. So instead of us just insulating in between the studs, we're trying to all this surface area. So all this surface area can really sort of add up to being anywhere between 12 to 15% of any sort of building is made up of the structural element, and it's normally the structural element that's going uninsulated. So we're really trying to insulate those areas. So in a typical wall, you know, you might put, you have your stud at every 600 millimetres. The wall needs to achieve an R 2.3 as a total R value in a commercial sense. This is. So if you had, say, an R2 insulation in there, where your stud is, you're getting like really where your concrete is and your steel stud, you're getting 0.4 of insulation. So your total R value is really dropping from R2.3 to say like an R1.9 or an R1.8 as a total R value. So the idea is we're really trying to sort of wrap that building and get that continuous form of insulation. So this is the picture which is our K5. So basically a rigid insulation board, and that'll have a rendered put straight over the top. So we do this quite a fair bit in residential buildings. Other forms of continuous in commercial is our cool therm with the clip and channel system.
Do you need to supply anything on the outside of that K5 panel to get the render to bind?
Yeah, we do. So we basically, so the process is on that K5 is we pretty much will put a primer on there.
Yep.
Once the primer is dried, we then put a base coat on. Once that base coat is still wet, we'd embed a mesh into it.
Yep.
Then once that is dried, we'll put on another two coats of polymer render, high polymer render.
Mm-hmm.
So the actual coating will end up being, you know, between 6 or 8 millimeters thick as a total thickness.
Yeah. So it's it was primer and then undercoat with the mesh, and
Yes.
then 2 coats of polymer.
So you got your primer.
Yep.
Once the primer coat is dried, then you got your base coat. Before your base coat is dried,
Yep.
it gets mesh embedded into it.
Mm-hmm.
And then once that is dried, then there's another 2 coats of render.
Has insulation got a lifespan? Does it wear out?
Well, it depends on what type of insulation you're really talking about. I mean, our cool therm, for example, you know, we actually warranty the R value, the actual inherent R value for 20 years. You know, you talk about bulk insulation, like you said before you got up in your roof, for example, there's a lot of dust that sort of settles in there. So like this insulation here, if you get a lot of dust settling all in here, well then the insulation becomes ineffective. So yeah, insulation does have a lifespan, and inside a lot of roof cavities, in most cases it needs to sort of be taken out, sort of vacuumed, and then new insulation put back in.
Why would you retrofit glass fibre with that?
Well, if you're going to, this on top of in your ceiling space, if you're going to clean the whole lot out, if you could get in there, of course, you need to have access. If you're going to get in there, you know, you have to pull all the old insulation out and then retrofit new insulation back in there. So just some of the options, yeah. But that pretty much brings. I just thought just to show you a couple of pictures of the other slide. I mean, a lot of the stuff is sort of doubled up from what you've already seen. We use on a school project. We used our insulated plasterboard on a school project, which is basically, I'll just get to it here, a K18, 10mm plasterboard, 50mm cool therm. It's got a reflective foil on the back of it, and that got used in a classroom type of construction. So
rake ceiling.
In a rake and ceiling, yeah. Yep.
That's good.
That pretty much brings me to the end of it anyway. Yep. So thanks for your time. Any other questions at all?
So, what about the normal life expectancy?
So life expectancy of insulation, yeah, it's a hard one. Depending on what insulation you're really talking about. If you went with a rigid board insulation, so for example, if I go back to this picture here, for example, if I go back to this picture here, for example, if you're using a rigid board, it's not going to sag. It's going to have plasterboard over it, so it's going to be pretty well protective. So something like this, I mean, realistically, I mean, you would expect to get 50 or even 100 years out of it because it's pretty well protected. You know, if you were to put a bulk insulation in your wall stud, I mean, what is the expectancy of that? I mean, I'm not sure because You know, what if you get it sort of sagging over time, or if it's on top of the ceiling, if it gets covered in dust. So it's really
So it
depends on what you're using and where it is.
okay.
But let's say on top of your ceiling, it's bulk insulation. You know, every 20 years you probably want to be pulling it out and replacing it if you've got a 20-year-old house. It'd probably be time to be doing it.
Coming up.
Yeah, well, that's right.
What type of failures that come across your profession?
What sort of failures do we get?
Installation regards, yeah.
Oh, depending, probably some of the failures you might get as far as insulation goes is maybe some of the fall delaminates. I mean, it's you don't get too many failures in insulation.
Yeah, I've seen issues in
with
in
the
houses.
sarking, yeah.
Yeah. Oh yeah. You got the
Yeah.
you got the issues with the sarking degrading over
Yeah.
time for various. Yeah. Maybe I should take note of some of those product names.
Yeah,
But
that's right.
see that hanging out in shreds in roofs.
The people don't complain about putting installation in and then they don't get enough installation, that sort of things.
Well, I don't know. I mean, I know from my own personal experience. I mean, years ago before I was in the insulation industry, I mean, I had a brick veneer house, and they insulate, in the walls of the brick veneer house. I know in the summer issues, I had that aircon going on flat out, but what are you gonna do? Who are you gonna go and complain to? You know, there's not too many people to really go and complain to, is there?
Yeah. But
you
also.
can't complain to the builder, but
Well,
Yeah.
you guys, I mean, the company-wise give, assure that this is going to be material, R value of this much, and
Yeah.
Talks about
I
that.
tell you what they are doing. That they are trying to tighten up on that sort of thing.
Yeah.
So they are introducing now what they call blower air door testing. So have you guys done your energy efficiency part of things yet?
Okay.
No, it's not something I cover in
Yeah.
here.
So pretty much what they are doing, I mean, at the moment, it's a requirement for houses to achieve a 6-star energy rating. So the way that they rate that is they will basically put it through an energy rating software package such as First Rate or Birds or Accurate, for example. And then the energy assessor will punch in all the information into all the data information into the software package. They'll have the perimeters and the zones of the house and the orientation of the house, and they'll have what type of glass that they're using, what type of insulation they're using, or what R value, and then that will give them a star rating at the end of it. So that will give them a 6-star rating. So some of the problem is with that. On paper you've got a 6-star rating, but if the insulation is not installed correctly, it's not going to work effectively, or if the insulator, or if the windows, or if the right glass didn't go in, which was on the energy assessment said it should go in, it's not going to work effectively. So one of the ways that they're trying to really tighten down this is they're going to introduce blower air door testing. So basically what they'll do, let's say a building like this, they'll close up all the doors or the windows, they'll put a large sort of canvas bag over the door. They'll have like 1, 2 or 3 fans on that canvas bag, and they'll pump air into the building. And they'll work out what volume of area there is in the building, and they'll try and work out how many air exchanges an hour that building will have. So a good building will have probably 8 air exchanges an hour, and a really poor building would have like maybe 20 air exchanges an hour. So with the new buildings now, they're looking at introducing this blower air door testing. So they're hoping that this is going to, tighten up the actual building industry and tighten up the buildings. So that way you don't have, cold air leaking into the building. So for example, you've sat down on a winter's day in the lounge room, you can feel cold air running over your feet, for example, in some houses. So.
So when the builder gives notification to the council that the building is complete, that's when. Yeah. So this is proposed to come in.
Yeah. So they're introducing it, like say 1st of May next year as a voluntary type, and the National Construction Code is going to say, well, it's now coming out every 3 years. So they're talking about it might be. Obviously, there's another cost involved with this. So the building industry is trying to keep the cost down as much as possible. So there's another cost involved in this. So they probably won't make it mandatory until another, 2 releases of the National Construction Code. So it might be another 6 or 9 years before it's mandatory, but next year it's going to be as voluntary. So yeah, they are trying to make it more energy efficient or make the building process better, but it's going to take time, I suppose.
Yeah. But in the next run of the National Construction Code, we can expect some changes in regards to insulation.
Yes, there will be.
Yeah, so we're looking out for that.
We're looking at taking into, well, I probably know more about the commercial than what I do about residential.
Yeah.
But they're looking at taking into account the overall thermal value of the wall and the window as one.
Mm-hmm.
There's a lot of in the commercial. There's some concessions now. If you have lighter coloured walls and roofs, you get some concessions where they're taking those concessions out. So for example, if you had a dark colour roof where it's at a solar absorption of above 0.4, for example, solar absorption. If you had a lighter colour that like a zinc loom or a white roof, you've got a concession. Well, they're taking those concessions away now.
Right. Yeah.
With lighting, pretty much if you were using LED lighting, you got a concession as well as far as your energy assessments go. Now they're assuming that everybody's going to be using LED lighting, so they're taking that concession out as well.
Yeah. And in terms of specifying the insulation for commercial projects, are architects and designers typically farming that out to insulation suppliers like yourselves, or are many of them taking it on themselves to go through that process?
As far as the energy assessments go? Or?
Yeah. Oh, well, just for the specification of the insulation.
Yeah,
with residential, it's fairly simple.
What we're finding a lot, a lot of building designers, in a lot of cases, they're just nominating an R value.
Yeah, right.
So what they're say building designer, they've drawn up the plans, they've selected their energy assessor.
Yeah.
So they send the plan to the energy assessor. The energy assessor says what value of insulation are they using. They might just write on the plans, R2.5 in the walls or R4 in the roof. They haven't selected what type of insulation so they're...
Yeah, then it's up to the builder to make that choice. Yeah.
And then normally the builder gets it and they sort of do what they want with it. They build it relatively to code, but it's just they'll just get an R2.5 bat or But one of the things I say to designers a fair bit is, we manufacture the insul break, which goes underneath your iron roof or your tiled roof, and it's pretty important to have a reflective insulation under your roof, as opposed to just having insulation on top of your ceiling. So one of the cases that we sort of talk about is so you've got your house type sort of as a construction with your house. Here's your ceiling here. A lot of people will put like an R5 on top of the ceiling, but basically, with the heat gain here on say like a 35-degree day, it will get like 70 degrees temperature in here, quite easily 70 degrees temperature. If you go back to that example here, where your bulk insulation is made up of like just strands of fibre, and so there's air pockets in between those strands of fibre, that's really stopping, reducing the heat. Once they heat up to 70 degrees, because this environment's 70 degrees, you're going to come home from work or later on in the day, you're going to have basically 70 degrees sitting up here. So what we say to a lot of the designers is put the air cell insul break under the iron roof, let it sort of dish in between the purlins by around about 40 millimetres to get that bit of air cavity in there, and you can literally reduce 20 degrees off this ambient temperature.
You're kidding.
No, absolutely. It's still 35 degree day, but instead of that being 70, you might only find it's 50 degrees in here. So although the house is still hot, but you've reduced 20 degrees out of here, so you've reduced 20 degrees out of your insulation, you're going to find it a lot easier to cool down. And it's the same thing in the winter. You have a heater on in the lounge room, there's heat coming up through your ceiling. As the heat finally does get past your insulation, if it hits a really cold attic space, it's going to dissipate really quickly. But if you've got, say, the insul break under your iron roof or tiled roof, and you're sort of trying to maintain some of that heat in that attic space, the heat's not going to dissipate so quickly. so the heat's going to stay in the bats
Yep.
longer as well. So you really want to try and get that balance of insulation.
Yeah, yeah.
You know,
Yeah.
What's the best way to, you know, they become more and more common, the old shipping container construction houses. Now, what sort of insulation would you be using for the walls on those?
We'll use our insulated plasterboard.
Yeah.
You know, a fair bit in those,
Yeah.
fair bit in those sort of constructions.
Could you use that on the outside?
You can use it on the outside. Insulating on the outside is a better way to go. You're going to get much.
Yeah, you're going to lose up space.
You're going to get a lot more energy efficient building if you try and keep the heat on the outside of the building as opposed, you know, let it get in and then try and stop it.
Yeah.
So insulating on the outside is a better way to go.
Could you put cladding on the outside, like, you know, where the
Well, you wouldn't put it straight on that, but you know, if you had a shipping container, probably the best way to go would be to, you know, maybe batten it over, say 600, insulate it in between it, and then put an iron cladding on it. That would be the way to go.
Yeah, so your shipping container basically becomes your studs.
Yeah.
And-
Oh yeah,
Yeah.
yeah. But yeah, if you were to screw some type of fixing, I mean, you wouldn't want to be putting exterior cladding onto that and then gluing it to the shipping container. I mean, we wouldn't really say that would be a great construction way of doing it. You want to have something solid to fix it too.
Yeah.
Yeah.
And, you know, these mobile houses that are built in yards, what's the most common sort of insulation they use?
Yeah, they'd be using between their wall studs, probably an R2.5 glass batt insulation.
Oh, yeah.
I would have thought, yeah. I mean, I know Superlock down there at Elizabeth West, I think they are. I know they're using like foam, injected foam in between their studs. They're injecting like a foam to try and get that continuous sort of nature of insulating, which doesn't sound too bad. So yeah, there's plenty of builders out there, you know, doing different things and trying to improve, you know, the energy efficiency of some stuff, so of the buildings. Yeah.
Cool. Well, we could probably keep you here all day, but yeah, we've got plenty to get done. So, yeah. So
No worries.
thank you very much for coming in and,
That's
and
all right,
sharing.
good on you. I'll leave some
Yeah.
of these data sheets here if you want.
Yeah.
So,
And yeah, and I've recorded this as well. So I'll get that recording stopped.
Oh, that'd
So
be
we've got
great,
the recording
yeah.
and I'll share that with the external students as well.
oh, yep, good on you. Do you want me to leave this information here with you?
Yeah, a little bit. Yeah. Yeah, that'd be great.
Leave that with you. You've already got that.